In the upcoming videos, we will delve into the rationale behind the inclusion of a correction factor in the sample variance equation, where we divide the value by n-1 instead of n. We will explore this question through three distinct approaches. First, in this video, we will conduct an empirical analysis. Moving on the next video, we will develop an intuition for this question. Our final approach will involve a detailed mathematical derivation. Why do we divide by n-1? In this discussion, we present the equations for variance, distinguishing between the population on the left and the sample on the right. Several key distinctions exist. The population variance is denoted by sigma squared, representing the true variance of the entire population, while the sample variance uses s squared. For the population equation, the sum encompasses all data points in the population denoted by an uppercase N, compared to the sample sum includes only the number of data points used in the sample, indicated with a lowercase n. The population average is denoted by mu, and for the sample, it is represented by x bar. Crucially, the denominator for the population divides by the total number of data points in the population. In contrast, for the sample, we divide by the total number of data points in the sample minus 1. The objective of this discussion is to unravel the rationale behind subtracting 1 from the denominator. We will explain this equation through three distinct approaches. First, we will employ an empirical analysis using sample data to validate the equation. Second, we will gain an intuitive understanding of this phenomenon. Lastly, we will utilize a mathematical derivation. Let's start with our first approach using an empirical process. For our data, we will utilize scores from a standardized test as an illustration. Consider a scenario where 10,000 students took a test with scores ranging from 0 to 100 points. The students achieved an average score of 70 points, a variance of 100, and a standard deviation of 10 points. The histogram visually represents the distribution of scores. Given the impracticality of querying all 10,000 students about their individual scores, our objective is to estimate the population average of 70 and a variance of 100 by collecting data from a small sample of individuals. Let's initiate the analysis by examining the average of both the sample and the population. For instance, we can randomly select 5 individuals and inquire about their scores. In this specific instance, the scores are 61, 66, 70, 78, and 81. Calculating the average using the appropriate equation, we obtain an average value of 71.2. This proves to be a good approximation to the population average of 70. To test the robustness of this approach, we repeat the process with another set of 5 individuals, resulting in a less accurate average of 60.2. By repeating the sampling process multiple times and creating a histogram of the averages, we can extract the average of this distribution, known as the expected value of the sample average. In this example, the outcome is 69.6. Very close to our population average of 70. This initial analysis leads us to the conclusion that the expected value of the sample average closely approximates the population average, demonstrating the effectiveness of the average equation where we divide by the number of samples n. Let's conduct a similar analysis for the variance, starting with an ideal version of the equation as shown here. Observe that we have two subscripts for the variance symbol s. The first mu indicates that we're subtracting the average of the population. We deem this an ideal situation, recognizing that in practice this information is typically unavailable, as having the entire population data would be necessary to calculate the population average. The second subscript is n, indicating that we are dividing the equation by n instead of n-1, which is the expectation. Continuing with our sample analysis, let's randomly select 5 individuals and record their scores: 63, 75, 78, 82, and 86. The population average is then extracted, yielding 76.8. Using the sample variance equation from the slide, we calculate a value of 107.6, closely aligning with the population variance of 100. To verify if this trend holds for all samples, we create a graph with the x-axis representing the value of the sample variance, marking the value obtained in our experiment. Repeating the sampling process multiple times allows us to construct a histogram. The average of this histogram, known as the expected value, is 100.05, remarkably close to the population variance. This brings us to our next conclusion. The expected value of the sample variance, utilizing the population average and dividing by n, closely approximates the population variance. Considering that in practical scenarios the population average is often unavailable, we will compare our results using the sample average as depicted in this equation, also known as the bias equation. It's worth noting that we have adjusted the subscript of the variance symbol S to include x bar, signifying the use of the sample variance. The subscript n is retained, indicating the division by the total number of samples. By extracting several samples of size 5 and calculating the variance using this equation, we can construct a histogram which tends to be skewed. Upon extracting the expected value from this histogram, we obtain a value of 80.4, notably lower than the population variance of 100. This leads us to the following conclusion. The expected value of the sample variance is lower than the population variance. If we can reduce the value in the denominator, there is a potential to increase the value of the sample variance. Now let's explore the outcome when we replicate this experiment using the following equation, which represents the true equation for sample variance, also referred to as the unbiased equation. Observe that the subscript of the variance symbol S now includes n-1, signifying that we are dividing by the number of samples minus 1. Once again, we will collect multiple samples of size 5 and employ this equation to derive the sample variance. Subsequently, we'll construct a histogram. Upon calculating the expected value from the histogram, we arrive at a value of 100.5, remarkably close to the population variance. This brings us to the following conclusion. The expected value of the sample variance, utilizing the unbiased equation with a denominator of n-1, closely approximates the population variance. Let's conduct one more experiment using the following equation, where we use the denominator of n-2. Note the change in the subscript of the variance symbol S, which now includes n-2. In this instance, we gather multiple samples of size 5 and visualize the data through a histogram. Upon calculating the expected value, we obtain a result of 134, significantly larger than the population variance. Therefore, our conclusion is that the sample variance is higher than the population variance when we use the n-2 denominator. Here's a side-by-side comparison of the 3 equations we employed, all involving subtracting the sample mean but utilizing different denominators, n, n-1, and n-2. Our findings reveal that the n-1 denominator yields the expected value closest to the population variance. Based on our experimental approach, we designate this equation as the best option. In conclusion, the expected value of the variance using the sample mean and the denominator of n is smaller than the equation utilizing the average of the whole population, unrealistic in practical sense, and the equation employing n-1 in the denominator. Both of these results serve as good approximations to the population variance. Furthermore, the population variance possesses a lower value than the expected value of the sample variance that uses n-2 in the denominator. Therefore, we have empirically demonstrated that the equation for sample variance using n-1 in the denominator performs well. This analysis, which is based on a sample size of 5, consistently yields similar results when we use other sample sizes. In our next video, we will delve into obtaining an intuitive explanation. If you find this content valuable, feel free to subscribe to the channel.